start the recording. Let's go ahead and share screen. All right. Desktop audio is recording the correct output. Cool. So let's just go through and start off. What exactly is a right-hand rule? And what sort of right-hand rules have you seen so far?
It's a easy way to visualize doing like the cross product between two things, because you need to have a right angle and what is the resulting vector from it.
Mm-hmm, exactly. And so what are some of the examples of right-hand rules you've seen so far?
The magnetic dipole with the current in a loop.
Mm-hmm.
Of course,
So how does that work exactly?
So you curl your fingers in the direction that the loop or the current of the loop is going. Say it's going, say for instance it's going like a clock and going clockwise.
Mm-hmm.
Then your thumb would be pointing into the page, I believe. So
Yep.
that's the direction of the magnetic dipole moment.
Exactly. So that'd be into the page, which is the little X. And what's another right-hand rule you've seen so far?
Let's see. So I guess since you didn't have it last week, then we would have talked about L and the current and the magnetic field. So that would be IL cross B.
IL cross B. So we have the wire in a magnetic field. And so how would we use our right-hand rule to know which direction the force is going to be in?
You would start your fingers pointing in the direction of the length or the current.
So let's say to the right.
Sure, and then transition them. So I guess like up if the not the electric field, but the magnetic field is pointing upwards.
Mm-hmm.
And that would result in your thumb pointing out of the page. So a circle with a dot in the middle.
Yep, exactly. So our pointer finger goes in the direction of the current. Middle finger or the rest of your fingers curl upward towards the magnetic field. Force, your thumb comes out of the page. And then that's also similar to if we have a single particle, right?
Mm-hmm.
And so we have IL cross B, and then we also have QV cross B, right? Basically same thing. Any other right-hand rules you guys have seen so far? I think this might be
the torque. Is it the torque one? Has
mm-hmm.
The magnetic dipole moment cross B.
Mm-hmm.
Is that right?
Yep. Formula sheet right here. It's good. I think the main thing I always stress is just don't forget about the formula sheet. And if you ever don't feel like you need to know things without the formula sheet, because honestly, having a formula sheet and knowing what formulas you need really helps. You're exactly right. You have the torque where you have the magnetic dipole cross B. Those are sort of the main right-hand rules you guys have seen so far. And welcome to Vij. Welcome, Kevin. We're just sort of talking about right-hand rules and the sort of right-hand rules you guys have seen so far.
God bless the right-hand rules. They're all confusing. I'm actually happy that the professor finally made a video about it, because it kind of clarifies what you need to do, I guess.
Yeah, it's definitely the part that most students struggle with. It's definitely what I struggled with most, because
I understand the rule, but I just don't understand the positioning of your hands.
Yeah, it's you just have to remember for each individual example of the right hand rule, you have to understand what way you have to orient your hands and which fingers correspond with what. And the way we usually teach it in the class is, let's take, for example, we have the IL cross B. We just have a magnetic field going upward, and we have the wire going to the right. Which finger is going to represent which?
Your index finger would be representing the wire, or the current, or in this case, I. And
Mm-hmm.
B would be your magnetic field, so that'd be your middle finger. And then F would just be your thumb.
Exactly. And as long as you know that for every single right-hand rule, you're golden. But don't worry if you do get messed up every now and then, because it happens to all of us. Especially it happened to me a whole bunch when I first started learning magnetism and stuff. And honestly, I only started feeling more comfortable with it when I actually started doing SI Pass for this class and actually having to be able to explain it to people. So,
Alright, that's neat.
yep. So there's that right hand rule, and then we also have the basic curl right hand rule, where if we have like, for example, the magnetic moment due to a loop of wire, or there's also one other example where you use the curl right hand rule. Do you guys know what it is?
Isn't it for torque?
The torque would be this first right hand rule again.
Oh, torque. Wait, it won't be torque. It'd be mu. I'm trying to solve for mu.
Well, that's what this one is we just talked about, where we have the current going around, and then we have mu coming. Well, in this case, the current's clockwise, so mu's into the page.
Yeah.
There's also, I haven't quite, I mean, it's mostly with chapter 18 with the Biot-Savart law, which tomorrow's session is going to be mostly focused on.
Oh, I haven't gone to that. I need to quickly get that one done.
What direction is a magnetic field going to be generated in for a straight wire?
It has to be perpendicular to it.
So it's always going to be perpendicular to the wire, and in what direction?
Either up or down.
And how do we know what direction?
What direction? It doesn't it? It has to make a 90-degree angle. It can be in any direction, but as long as the angle is 90 degrees, then you're golden.
But so let's say we have our current coming out of the page here, right? Is the magnetic field going to be to the right up here?
No.
No, but it fulfills all your requirements, right? As long as it's a 90-degree angle, you're good.
Well, no, it's not like that, but it's kind of hard. But the current, your magnetic field would have to be up. If I'm
Above?
doing it correct.
Up here?
Yeah, up. Yeah, it'd be pointing up in the y direction, so it'd be straight up instead of to the right.
That's not right either. Anyone want to come in and help Divish?
If you're so you have your thumb pointing in the direction of the current, right? So our thumb would be pointing to the right, yeah. So whichever way you curl your fingers, depending if you're on the top, you curl your fingers towards you, so that would be out of the page. And if you're below the
No, in this case, the current is out of the page.
oh,
Current's out of the page.
wait, what does the arrow represent?
That was just the arrow doesn't matter. It was Divish was saying that the current would be the magnetic field would be to the right, and I was saying like, is that right? It fulfills all your requirements, but
Oh, sorry, I thought the arrow was the current. So if the current is coming at you, then your thumb is pointing out of the screen, and the magnetic field would be going in a counterclockwise around it. So depending on where you are, you can look at the tangent line to it.
exactly. Yeah, that's the other curl right hand rule I was mentioning earlier,
Oh, okay.
where we can curl our fingers to find the direction of the torque of the magnetic moment, or we can also point our thumb and then our fingers curl in the direction of the magnetic field. So welcome guys, welcome everyone that's coming in. If anyone hasn't already filled out the attendance form, you can find it in the announcements tab, or I guess I can also put it in session text real quick. Bada boom, bada bing. But so these are the main right hand rules you guys will see. So let's go ahead and actually hop in and do an example. So we're going to have, let me actually go ahead and move this over slightly. Boom, perfect. So we're going to have a circular loop of current with radius 2 centimeters, and it's going to be 200 turns of current. And it's going to be placed in a uniform magnetic field of 5 Teslas. Arbitrary numbers, who really cares? I'll probably just refer to them as B and N turns with radius R. The current through the loop is going to be 50 milliamps. We'll just call it I. Who cares about the numbers until the very end? So how would we actually go ahead and determine the direction of the magnetic dipole of this loop? Everyone just shout out. So if we have our loop looking like this, with current going around in this direction, what direction is the magnetic dipole going to be in?
Would it be pointing inwards? Wait, no. Actually, I'm a little confused there.
We spent 10 minutes talking about right-hand rules, goddammit.
You said the current is what the arrow indicates, right?
Yeah, this is the current I for our loop.
And we're trying to find magnetic what? Force or field?
The magnetic moment.
A moment. Okay. 1 second. Would it be out of the page?
Yep, exactly. It's going to be...
Because you can use your 4 fingers to curl with the movement of the current, and then you figure out that the magnetic the magnetic is pointing out.
Yep,
the
exactly.
page.
Exactly.
Alright.
So we have our magnetic moment mu coming out of the page. That's how we would figure out our direction of our magnetic dipole moment. Also, welcome, Shadia. So, let's go ahead and let's say that our magnetic field is going to be, I don't know, what direction do we want to have it in? And we'll just give a random direction. Let's say our magnetic field is going to be straight downward. This is going to be our magnetic field. So, let's go ahead and let's take 5 minutes. I want you guys to go ahead and draw the loop so that the magnetic field is perpendicular to the magnetic moment. And then what would be the magnetic torque acting on the loop in the position? Let's say both the magnitude of the torque and also what direction the torque is in. And then also, what direction would that cause the loop to rotate? Let's take 5 minutes, then we'll talk through it. So draw the loop so the moment's perpendicular and find the torque. All right. So, how would we go ahead? There's actually multiple options here. How could we actually go ahead and draw our loop so that the magnetic moment is perpendicular to the field? There's multiple options here. There's multiple right answers. Couldn't we just, for example, just take our example from before, where our loop is going counterclockwise? Would that work?
Yeah, that would work.
Mm-hmm.
That
Exactly.
means your current would be pointed towards the left, and then when you rotate I to the left side, you get your magnetic momentum pointed out of the page. Can't you also have your current pointing to the right, or clockwise in this case, and
Yep.
then you have your magnetic momentum pointed towards the page?
Yep, exactly. We could have our current we could have our current clockwise, we have our current counterclockwise, and then we could also, for example, it's hard to visualize it, 3D drawing in 2D, but if we have our current doing something like this,
Well, your magnetic momentum would be pointed towards the right,
yep, exactly.
and vice versa would be left.
Yep, exactly. All these examples, as well as any angle in between any of them, is all going to be correct. So as long as our magnetic, if this is the z direction, negative z direction straight down, as long as our magnetic moment is in the xy plane, we're good. And so what would be the magnetic torque acting on the loop in this position? How would we go ahead and calculate the magnetic torque?
Well, since they're perpendicular, can't you just do mu times b?
Mu times b? Yep, so our torque is, let's see, what's the actual equation for torque with the vectors?
It'd be mu cross b.
Yep, is equal to mu. And so why can we simplify that to just mu times b?
Because when you expand it, you get mu b sine of theta, but the angle between them is 90 degrees. So sine of theta would be 1.
Perfect. I literally couldn't have explained it better. So our torque we know is going to be, or at least our magnitude of our torque is going to be mu times b. And how do we get the value for mu with what we're given? We're given the radius, we're given the number of turns, we're given the current through the loop.
Oh, wait 1 second.
We can find the area and the number of turns.
Mm-hmm. And
mu equals number of turn times current times the area.
Yep, exactly. Mu is equal to the number of turns, which in this case is 200, times the current in the loop, times the area. What's the area of a circle?
2 pi r.
2 pi r? Or
No, that's circumference. My bad.
Yeah.
Pi r squared.
yeah, pi r squared. Ni pi r squared b. And we could plug in all the numbers, but who cares about that? I'm sure you guys can do that. So that's our magnitude of our torque. And now, what would be the direction of our torque? Let's say for this example where our magnetic moment is to the right. What direction is the torque in?
Torque be pointed into the page,
And why is that?
because if you're using your pointer finger to point towards the magnetic momentum, and then you have B being your middle finger pointed downwards, then your thumb will point into the page.
Exactly. Boom. So we know that for this example, our torque is going to be into the page. And for one other example, if we have our magnetic moment here coming out of the page, what direction is the torque going to be in?
It's gonna be in the right.
Yep, exactly. Same rule. Point our index finger out of the page, curl our middle finger down. Try not to feel like your wrist is breaking while doing this, and you'll find that your thumb is pointing to the right.
All right.
So, and now what direction is that going to make the loop rotate? If we let the torque rotate the loop, what direction would it rotate in?
Wouldn't it rotate counterclockwise?
What do you mean counterclockwise?
1 second. So if torque is going this way. Wait, Okay, I think I'm kind of confused, I guess.
It's rotating like top over bottom. It rotates about the axis that the torque vector is on.
Exactly. And how do we know what direction it rotates?
The right hand rule.
Right hand rule! Woo! So for this example, if we have our torque into the page, we point our thumb in the direction of the torque, and then we curl our fingers around to find that our loop is going to want to rotate this way.
Oh, okay, I see. Oh, okay, that makes sense.
And then for this example here, we found our torque was to the right.
Yeah. So if it would want to curl forward.
Exactly. So sort of,
All right.
this arrow is sort of supposed to be like coming out of the page and down. So you'll find that for all these examples, the torque is always going to make the loop rotate so that the magnetic moment goes towards B. That's something that, honestly, don't worry with right-hand rules. If you just memorize that, magnetic moment always goes towards B, then you should be good for most of what you'll see in the class.
So if it's like a torque-related question, like asking how would it rotate, would you just say you just think that the current goes towards B?
Not the current, but
Or the magnetic movement, I guess?
the magnetic moment. Yep. Magnetic moment is always going to rotate towards B. And we found that by doing right-hand rules. And basically now you guys should be pretty good and comfortable with the right-hand rule. So now let's go ahead and let's take 5 minutes again. And let's go ahead and draw the loop in the magnetic field such that the torque on the loop is 0. And there's going to be two options here. And then what's going to distinguish these two orientations? Let's take 5 minutes, then we'll talk about it. All right, so what are two ways that we can orient our loop so that the magnetic field, so that the torque on the loop is 0 in the magnetic field? What are our two options?
Well, the dipole moment and magnetic field would have to be parallel. So I figured our two options would be if mu and B are in the same direction and in opposite directions.
Exactly. So what would those look like for our loop?
I drew the same loop, and then I drew like the loop in like the XY plane with mu coming out of the page,
Mm-hmm.
and then you could draw the magnetic field as either out of or into the page.
Yep. So these are our two options. For the first one, our loop is going around like this, and that would mean our magnetic moment would be coming straight down. And then this other one, where our magnetic moment is straight up. So why did you want them to be parallel to one another?
Well, in that case, the angle between the dipole moment and the magnetic field is 0 if they're or 0 or 180, and in both of those cases, the sine of 0 or 180 equals 0.
Yep, exactly. Remember how the magnitude of the torque is mu cross B, which is mu B sine theta. If sine of theta is 0, the torque is 0. Exactly. So let me just label these as a B. This is D. And so how are these two orientations different? Like, obviously, first of all, one's parallel, one's anti-parallel. But what does that mean contextually? It's a bit vague of a question, but what were to happen? So these are both torque is 0, so these are both equilibriums, right? How are the equilibriums different? Divish, did you want to say something?
How the equilibrium's different. So one makes 180 degrees, and the other makes like 0 degrees. So, I think it's just based off of the stability, I guess. I'd say.
Mm-hmm. Exactly.
And like I know that 0 degrees is stable, whereas 180 degrees is unstable, and that's just based off of the equation of mu times b sine of theta.
Mm-hmm. And so, what do you mean stable and unstable?
Like I think it has to do with the potential of it, if I remember the lecture correctly. Okay, 1 second. Let me go back. I think I wrote that down somewhere here. Oh, I think it has to do with high energy and low energy, right? Huh. I don't remember, but all I know is that the zero is stable and 180 is unstable.
So basically, what you're saying is if we were to rotate these manually, like just a few degrees off, what would happen? Like,
I think you create like so you rotate the magnetic momentum and magnetic field a few degrees off. You create some kind of torque, I guess.
mm-hmm. And what is that torque going to do? Like, let's
It's
say we take
gonna
this
rotate.
first one and rotate it so that it's like this. What's going to happen?
It's gonna rotate the it's gonna rotate it.
To where?
Oh, it rotated. So torque is this way. 1 second. Torque is pointing that. It rotated. Crap. Actually, It rotated towards. Oh wait, my bad. It rotated towards the magnetic field.
Exactly.
think-
Matthew,
Yeah,
do you want to?
okay.
Did you want to sort of elaborate?
Yeah, I was just thinking about it like it's a stable minimum, so any like deviation from that is gonna generate a torque that accelerates it towards that minimum of 0 degrees.
Exactly. And so remember from before where all our examples, the torque is always rotating the magnetic moment towards the magnetic field. That's the case for every example. Keep going, Matthew.
Yeah, whereas if it's like if the dipole moment is in the opposite direction of the
Mhm.
magnetic field,
And let's say we
the
change
torque
it just a
generated-
bit.
Yeah, the torque generated is going to orient it even farther. It's gonna like magnify that deviation.
Oh, okay. So that's why one is unstable and the other is stable.
Yeah, so the
Because
0
of
degree
the
one,
Difference in torque.
exactly. The 0 degree one, if you offset it slightly, it's just going to return back to 0 degrees. The 180 degree one, if you offset it even just by the tiniest fraction of a degree, the torque is going to eventually make it rotate all the way back around. It's going to fall all the way down to 0 degrees, which is the stable equilibrium. That's the main difference between them. And then also you have the case with the potential energy and the work being done on the loops. That's actually what we're going to take a look at in the next example. Does anyone have any questions about this before we move on? Any last comments?
No, I think we're good.
All right. So let's go ahead and take a look here. So we're going to go ahead and place the loop in the magnetic field so the magnetic moment is in the direction of the field. So we're essentially starting in this first configuration. So if the loop is rotated around so that the magnetic moment is anti-parallel, so we're going from this configuration to this one, how much work is being done by the loop, on the loop, by the field? Let's say 5 minutes, then we'll talk about it. So how much work is being done on the loop by the field? Going from position 1 to position 2. All right. So we're taking our loop and we're rotating it from position 1 to position 2, parallel to anti-parallel. How much work is being done on the loop by the field? I guess the first question is our work done going to be positive or negative? And why?
I think the work will be, let's see, because it's being moved to the direction of the magnetic field, it'll be going down the hill in like that kind of sense. So it'll be losing energy. So I think the work done will be negative.
So you got the right answer. I think your wording was a bit weird, at least personally from the way I think about it. But you're right in the sense that it's going to be a negative amount of work. I think the way you understand it is totally fine. But anyone else want to give their explanation as to why it's negative?
Is it going from low energy to high energy? So you are putting in work. So you are doing positive work, and therefore, if you are doing positive work, then the system is doing negative work because it is gaining energy in that.
Exactly.
Is that right?
Yep. That's how I would think about it. So, or another way to think about it is we're going against the direction that the field would naturally do work. So it has to be a negative work. So naturally, it would never make it go from parallel to anti-parallel, right? It has to be some sort of exterior force. In this case, our, make-believe, manually moving it from parallel to anti-parallel. And so that's against the natural force of the torque. So that means that the work done by the field in the terms of torque is going to be negative. And so how do we actually calculate that total work done? This is something Devise was mentioning earlier with potential energies. Some other people mentioned potential energy as well. First of all, how do we relate potential energy to work?
So the total amount of potential energy when the loop is in say opposing direction with the magnetic field, it would be the total amount of work done. I mean, sort of. It would equal that in magnitude.
All right, but that's if we define our bottom position as 0, right?
Right.
Does this class define the bottom position as 0?
You tell me, I don't know.
There, once again, this is something that we haven't really done too much in this session, but I always stress it. Praise be, worship the equation sheet. You'll find your answer in the equation sheet here.
Isn't 90 degrees the zero potential energy?
Exactly. 90 degrees is our 0 potential energy. That's how we've defined it. And so what is the potential energy, by the way? How do we get the potential energy from what we're given?
Isn't it the equation, I guess?
Yeah.
Are we talking about the equation?
Yes.
Yeah, it'd be negative mu times b cosine.
So our potential energy U is equal to mu times b times the cosine of the angle.
Yeah.
Or in this case, it's the dot product, which
Dot product.
then turns into a cosine. Exactly.
Yeah.
Is equal to negative mu dot b, which is equal to negative mu b cosine of theta. So, how do we actually find the total work done if we know our potential energy at any point?
Just multiply by a negative, I guess.
Not necessarily. Because we're going from the bottom all the way to the top, right?
Oh, we're going from the bottom to the top.
So what's our potential energy initially?
It'd be the maximum, I guess. Or wait.
Is it just like negative mu times b?
Yep, exactly. Because our angle is 0, right?
Oh.
Angle is 0. This cosine becomes 1, so we can essentially just ignore it. So it's just negative mu times b. So we'll call it u1 is equal to negative mu b.
And then your mu2 would just be negative mu times b times negative 1 because it's 180 degrees.
Exactly. Cosine of 180 is negative 1. Cancels out with our negative, so we get a
So
positive
if you
mu
do
b.
the difference between them, you'd get 2 mu b.
So our total change in potential energy is plus 2 mu b. Exactly. So how do we get the work done? How does work relate to the change in potential energy? Go ahead, Matthew.
Are we talking about work done by the dipole or the magnetic field?
By the magnetic field on the dipole.
On the dipole. So work would just be the opposite of the potential energy in this case.
Yep, exactly.
So
The-
I have a question. If it's work done by the magnetic field, what would it be then? Not magnetic field. I meant to say dipole.
I mean, I guess it would be equal and opposite force. You could make that argument. But the reality is there isn't really a work being done by the dipole on the magnetic field. Because it's a magnetic field. It's like... It's sort of... It's not really like a physical quantity that you can do work on. And in this case, we're just defining it as straight downward. And nothing can affect it.
That makes sense.
But so our work, if we remember back from physics 121, work is equal to is equal to the change in kinetic energy, right? And then we know our total change in kinetic plus our total change in potential has to equal the total non-conservative force, which in this case is 0. In most cases, you'll see a 0. So that means it's equal to the negative change in potential, which is negative 2 mu b. Boom. That's how we get our total work done by the field on our loop. And so then, real quick, what would be our work done if we rotate from anti-parallel to perpendicular? So let's say something like this. So we can draw this. Our current's going to look something like that. Rotating from 2 to 3. What's going to be our total work done?
Well, we defined 90 degrees as our 0 potential. So we're going from U2, which was UB, to, let's say, U3, which is 0. So we're just getting the opposite of negative UB.
So it'd be just positive mu b. And so, real quick, why have we defined 90 degrees as 0 again?
Because the cosine of 90 is 0.
Yep, exactly. Our dot product and cosine of 90 is 0. So, yep, so our work for, this is G, this is F, work is equal to positive single mu b. Because that's our change in potential energy goes from positive mu b to 0. Work is negative change in potential energy. So negative, negative mu b, positive mu b. Does anyone have any questions about this?
No. Makes sense.
I'm still kind of confused on that. The direction where how we made the work negative. Does that mean like if the work is the opposite of that potential energy, does that mean the magnetic field has potential energy? Because I was thinking of it as like the dipole moment was the thing that had the potential energy.
Yeah, the dipole moment does have the potential energy.
But the magnetic field is the thing that does work.
Yeah. And so the magnetic field does the work on the dipole, changing its potential energy.
But those are I'm just wondering, like, why is it?
So for the first
Why
example,
is,
it's
like, the change in potential opposite to work? I was still kind of hung up on that.
remember back in Physics 121 with how are kinetic and potential energy related?
Well, and I think I get that, but like, isn't that when you have the work done by the dipole? But in this case, we're talking about the work done by the magnetic field because it's the potential energy of the dipole.
Mm-hmm. It's honestly, I understand why you're confused, and I guess literally the only way I can think of it is back when I was learning this is just it's like let's say you take a 1 kilogram ball and you lift it up let's say 1 meter, and so how much work is being done on the ball by you? Well, it's the 1 kilogram times 1 meter, right?
Yeah, but that would be like positive because you're lifting it up.
Yeah, and so the work done on it by gravity would be negative, if that makes sense, because we're going against the natural direction of gravity.
Okay, that makes sense.
Yeah, it's one of those things where honestly I hate it because I hate how it's defined like that, because it's like, well, the field isn't the thing that's doing the work, it's us rotating it manually that's doing the work on it. But it's like,
Yeah, but the field is applying a force in the opposite direction that it's moving.
yeah, so basically if we move against the direction we would naturally expect it to move, it's negative. If it moves in the direction we would expect it to, like in this example, it's positive. Divish, did you want to say something?
No.
Okay, I just saw the little green thing flash up a few times there.
Because I think it's just my mic is really weird. It's just really sensitive sometimes.
Yeah, I just couldn't tell if I was like, because it seemed like every time I was just about to start talking, like it popped up for just a quick second.
It's because, I don't know, my mic keeps on picking up the headphone volume, so it's like,
Yeah, I mean, I'm not hearing any feedback, but it was just like I sort of feel like, oh, am I cutting Divish off here? Like every 2 seconds, what's going on? All right, well, that's pretty much it for stuff I had prep for today's session, and I do have an assignment I need to get done by 3 o'clock. So I'm going to go ahead and wrap the session a bit early today. Hopefully this helped you guys out a bit. Right-hand rules and directions of torque and whatnot are definitely I'd say the most difficult conceptual stuff. At least in the sense that it's really hard to actually lean back on the math because you still have to conceptually understand right-hand rules. And most of the rest of the class, you can forget about understanding the conceptuals and just rely on the math. But in this case, you still need the right-hand rules. But hopefully this helped out a bit. Tomorrow, I'm going to be doing a session focused on the Biot-Savart law, aka the BS, the bullshit law. Definitely one of the more annoying things in the class, but hopefully this helped out, and hopefully it helps out for your quizzes on Friday. So, thanks guys for coming. Have a good day.
you too.
Thanks.
Mm-hmm.
Thank you.